Okay, my last chance today to clear things up. Everything going back to the first day. Let me remind you. First day we talked about probability and counting. Remember, permutations, combinations, the multiplication principle, and deciding when to use which. And the reason we did those counting problems is so that we could do probability problems. If the committee is formed at random, what's the probability that George is on it? Things like that, way back when. Remember conditional probabilities. Given that one event occurs, then what? An independence. Okay. First came up in connection with independent events, where being given an event perhaps did not affect one's view of another event. And later we talked about independent random variables. Where knowing the value of x doesn't affect one's assessment of the likely values of y. And then so these are basic concepts that came up early in the course. And then we talked about 7 distributions. Well, so let me remind you what those 7 were. The first one we talked about was binomial distribution. And that has still been coming up ever since. Multinomial distribution is very similar. Geometric distribution closely related to the binomial distribution, but it's counting a different thing. Poisson distribution. Well, these were discrete, but then we've also talked about some continuous distributions. The uniform distribution, which perhaps is less fancy than the others. Exponential. And of course the normal distribution that has come up in a lot of places. Anyway, there are those 4 limit theorems. The one we've used most is the central limit theorem for sums or averages of independent, identically distributed random variables. And 3 others. Markov's inequality, Chebyshev's inequality, and the law of large numbers. And section 12.7 on data and confidence intervals. And which, for confidence intervals, we draw on the central limit theorem to tell us what to do. Speaking of section 12.7, let me list 5 things that we should all know about analyzing data. So this is the section that provides our interface with your statistics course. We talked about how to find the sample mean and understanding what the sample mean is telling us. Specifically, its expected value is the mean, where we have independent, identically distributed measurements with mean mu. So by the law of large numbers, for large n, we figure x bar should be telling us pretty much about what the mean measurement mu is going to be. And where these independent, identically distributed measurements have standard deviation sigma, we know the variance over n. So it's standard deviation of sigma over the square root of n. Then there's also the sample median, which has made a brief appearance. There's how to find the sample variance. S squared. Well, we had a couple of formulas for S squared. Two equivalent formulas for S squared. And then there's understanding what the sample variance is telling us. Is the expected value of S squared is sigma squared. So by the law of large numbers for large n, these have a high chance of being close to each other. And then if we divide by the square root of n, take the square root of S squared to get the sample standard deviation. We can get the standard error, and want to understand what that is. Should be close to the standard deviation of the sample mean. And so number 5 on our list of 5 is knowing how to get confidence intervals. Well, if we know the actual standard deviation of the measurements, we can use that. If all we have is the data, well, we figure S should be close to sigma, and we can use that in getting our confidence intervals, say, 93% confidence intervals, whatever. And then there's understanding what a confidence interval is. Say 90, let's not always use 95, 94% confidence interval. Interval from A to B, say. That's telling us a certain probability. The probability that the mean measurement, mu, is in that interval is about, there were some approximations involved, is about 94%. Well, continuing this list of 5, there's adapting to the special case of binary measurements. Things up to here apply to measurements whether they're binary or not, but there's some special things that apply to binary measurements. We had a formula for the standard error. That came up in the binary case. Well, some frequently asked questions. One question that comes up sometimes is, will the final exam be easy or hard? The answer is yes. Perhaps some of each. We want something for everyone. There's a rumor that my final exams are hard. I like this rumor a lot. I spread it myself. I encourage you to spread it. Then you'll be ready for anything. Another question, when to use the histogram correction? Well, if we're doing the normal approximation to the binomial, we should always use histogram correction for greater accuracy. But that's pretty much the only time that we've insisted on using it. When should we use that worst case estimate for, I should write some of this down. We've sometimes said things like, well, we don't know what the standard deviation sigma really is. There's situations in which we have said, at worst, it's going to be a half. What situations? It's only when we're looking at binary variables, 0, 1 range. And we have no information that would give us some better idea of what the standard deviation is. So that means, yeah, we don't have empirical data. Because if we do have empirical data, then we could look at the sample standard deviation and perhaps get a better idea. Or no other information as to what sigma might be. For confidence intervals, what if we want, say, a 96% confidence interval? That means we want a number which we usually call z, our z value, for which the probability that some random variable with a standard normal distribution in absolute value is less than or equal to z will be 96%. So how to determine that number? Well, we look in our table on page 919 for a number phi of which is going to be 0.98, not 0.96, 0.98, because phi includes the left-hand tail here. If the middle has area 96%, the two tails have the other 4% and split between them. And our table says to use 2.05 or a little bit more than that, but 2 decimal places get 2.05. Well, speaking of questions, are there other questions that people wanted to bring up about the final exam or such? Yes. Yeah, if we're using the table, and the table lets us get these 2 decimal places, but if we look at the table, we see it should be a little bit more than that. So if you just take the closest number that the table gives us, that's going to be enough. We do not insist that you use interpolation, which is an obsolete skill because people now use calculators anyhow. Now, okay, if it's a 50-50 tie, if the thing you're looking for is right in the middle of 2 entries, well, I hear some people will use one of the numbers and some people will use the other one, and we'll take either one. Let's do, sorry.
One of the homework, they talk about histogram correction, and one of the problems when it asks us to use the central limit theorem to approximate the probability of something, should we use the histogram correction in that case? And also in that question, we've used Chebyshev's inequality, and we could use the histogram correction of that as well. So like adding 1/2 on both sides, and adding 1/2.
Okay.
Should we use it in those cases too?
Well, okay, the first question, there was a homework problem that said use the central limit theorem to approximate such and such. if that such and such turns out to be the binomial distribution, yeah, then we're, the central limit theorem, of course, gives us the normal distribution. Yeah, so that's the normal approximation to binomial. So we're going to use the histogram correction in that. That's pretty much the only place where we insist on the histogram correction. The other cases, yeah, an argument might be made for where we're approximating an integer valued thing by a continuous random variable. We could argue over it, but the one place we insist on is the normal approximation to binomial distribution. Well, let's look at a probability problem concerned with a phenomenon sometimes called clustering. Let's assume that each person in some population has, over a year's time, some chance of developing basal cell carcinoma, say 1 in 400. The actual probability may be a little less than that, but this will make the arithmetic easy. Basal cell carcinoma. Well, let's look at Westwood. And let's assume, and Westwood is not a precisely defined community, but so let's assume its population is 10,000. Well, we figure that in the coming year, some of these 10,000 people may develop basal cell carcinoma. How many? Well, it's reasonable to assume independence of from person to person. One person develops it, that doesn't mean that their next door neighbor is more or less likely to have basal cell carcinoma. So we can apply the binomial distribution. We have these 10,000 independent trials, each with the same success probability. As usual, using the word success rather casually to mean, yes, does develop basal cell carcinoma in the coming year, 2009. So the expected number of cases in 2009, well, say, using S for the number of successes, number of cases in these 10,000 trials, we know binomial distribution. It's n times p, 10,000 times 400. Yeah, so we expect 25 cases, and the variance, well, we know how to get the variance in the binomial distribution, n times p times 1 minus p. So that's a little bit less than 25. 24.94 if you want to be fussy. So the standard deviation is about 5, a little bit less than 5, 4.994. Question: what's the probability that in 2009 we get 40 or more cases? In the coming year. Well, without doing much calculating at all, your reaction should be that probability is going to be really small. Because the mean is 25, standard deviation about 5. 40 is 3 standard deviations above the mean. And we know that that's pretty unlikely. is 25 plus approximately 3 standard deviations. Sigma is about 5. But let's see what the numbers are. Probability of 40 or more. Well, it's binomial. It's probability of 40 or 41 or, all the way up to 10,000. But of course, we're not going to work those out one at a time. We'll use the normal approximation. It's about the probability, at least 39.5. Normal approximation to the binomial. We always want to use the histogram correction. And for a random variable with the normal distribution with the same mean and the same standard deviation as S. So we want to standardize. Change from S to X because this now has the normal distribution. And so we want to standardize. We'll subtract the mean. From both sides, so we have an equivalent inequality. We divide by the standard deviation, which is just a little bit less than 5. So now we have the standard normal distribution, and we can look up the values in our table. Okay, so we have 14.5, and we divide by 5. About 2.9. Almost off the edge of our table. Probably Z is 2.9 or more up to some large number that would be way off our table. Yeah, so we look up 2.9 in our table, but what we want is 1 minus that. Well, so I did look that up in the table. And our first reaction was right. It's pretty unlikely that Westwood in 2009 would have a number of cases that's 3 standard deviations above the mean. Well, so if they do get 40 cases next year, people will be pretty suspicious that there must be something other than random effects going on. But now let's look at part B. California has a lot of communities of size 10,000. Suppose we have a list. Say of 3,000 communities, each of population 10,000. But, non-overlapping. These are 3,000 different communities. And we still assume independence from person to person and hence community to community. What's the probability that in the coming year at least one of these communities will have 40 or more cases of basal cell carcinoma? For any one community, we took Westwood, we called it Westwood, but it would be the same for any community of population 10,000. Chances of getting 40 cases was pretty small. 1/5 of 1%. But if we take a whole bunch of communities, now what? Well, it's still a binomial situation, but a different binomial situation. $3,000 trials, which we assume are independent, and we know the success probability for any one trial, 1/5 of 1%. So the probability of getting at least one success, there's at least one community that's going to have a whole cluster of cases. Well, let's look at the complement. The probability that all 3,000 cases all 3,000 communities escape having 40 or more cases. And so that's 1/5 of 1% less than 1. Yeah, but raised to the 3,000 power. So we have to ask our calculator what that is. It's almost 1. Yeah. You take this number and raise it to 3,000 power, it gets very small. It's like 1 in 300. This much, when you work it out, is roughly 1 out of 300. It's pretty unlikely that that all 3,000 communities will be able to avoid having a cluster of basal cell carcinoma cases. Well, the point, the problem, yeah, this comes up in epidemiology. If you look at any one community, it's very unlikely of getting a cluster of cases. But if you look at things more statewide, it's almost certain, very high probability, that some community out there will get a cluster of cases. Well, end of this problem, let me look at a completely different problem briefly. Yes. To bring this board back. Well, okay. It's a binomial random variable, probability of 40 or more. Okay, I could tell my computer to just apply the binomial distribution and do it for 40 and 41 and 42 and 43 up to 10,000. But if I'm going to do it by hand or even with a hand calculator, it's going to be much easier to use the normal approximation to the binomial. It's if we want an approximation to the binomial, we'd use the normal one here and not the Poisson approximation, because NP is more than 5 and the expected number of failures is more than 5. So the normal approximation would be the better choice. One more problem. Going back to earthquakes, and speaking of the Poisson distribution, let's assume that major earthquakes worldwide, and not just looking at Southern California, but globally, for some criterion of what counts as major. Follow a Poisson process. With an average rate of 0.7 per month. But a Poisson process, so earthquakes just hit now and then, independent of the past, no special pattern. And we ask, well, what about 2009? Well, the expected number of earthquakes, major earthquakes in 2009, rate is 0.7 per month. If we look at 12 months, we expect 8.4 earthquakes in 2009. But that's not the problem. imitating that problem about typographical errors in a book, what's the expected number of months with earthquakes? That's going to be less than 8.4 because we could have a bunch of earthquakes in 1 month. And, well, let's look and see what the expected number of months. And to keep our lives simple, we'll assume that all 12 months have the same length. Now, we know that's not quite right, but they're about the same length. And for any 1 month, the probability of having an earthquake well, that is, to be more exact, a probability of having an earthquake or more, qualifying as a month with earthquakes. Would be, well, we apply the Poisson distribution. It's easier to look at the complement. The probability of not having an earthquake in that month is e to the minus 0.7. Right, because we're looking at 1 month here. And for the probability of 0 hits in a time period of 1 month, it's e to the minus lambda, okay, lambda to the k over k factorial, but if k is 0, it's just e to the minus lambda, e to the minus 0.7. And we're subtracting that from 1. Okay, so what I wrote down here is I have to squeeze in 1 minus the probability of 0 earthquakes. And we could ask our calculator what this is. But what we want is now for 12 months, the expected number of earthquakes. Well, this part of the problem is Poisson. Now we have to shift our thinking, because we have these 12 independent trials. And where success means, yeah, there is an earthquake or more than one in that month. So the expected number of successes in 12 months is 12 times the probability of success probability for a month. One minus e to the minus 0.7. And sooner or later we break out our calculator to see what this is. It's about 6 months. That is, the expected number of earthquakes for next year is 8 and some more, but the expected number of months is only 6. It's smaller because you could get more than one in a month. Well, if you're wondering how can I get 7 distributions into an exam, maybe I can get more than one distribution into a single problem. Okay, got to stop there. Thanks for your attention.
Thank you.